Let's talk now about backpropagation through time. So this is often initialized BPTT. Backpropagation through time is really just normal backpropagation. So let's look at our diagram of backpropagation. So we have H0 coming in here through, let's say, WHH. And we have X1 coming up here through WXH. And those, of course, get combined. And then the output of this goes up through WHY into Y hat sub 1. And then this also comes across as H1 to, again, WHH. X2 comes up, Y hat 2 comes in. We have WHY, again coming up, and this comes out H2, and so on. All right, so this goes all the way through until we get to X sub n, assuming we have a sequence of length n. We have our W, XH, W, HH, WHY, up to Y hat sub n. What I'd like to do is add a bit of additional notation here. Piece of notation that just shows what time step it's used at. So this is WHY at time step 1, this is WHY at time step 2, WHH at time step 2, WXH at time step 2, all the way to the time step n. Eventually, right, we've got some loss function. And that loss function is feeding in information from all the y hats. Some loss functions, like the loss function where we're looking at polarity of a Yelp review, may only care about y hat sub n, but the general case we care about all these. And what we're interested in finding now is the partial derivative with respect to each one of the matrices and also the biases. It's really no different from normal backpropagation. We basically are going to take a particular weight matrix, like let's say the WHH, and we're looking at all the paths to it. And then we're going to just calculate the derivative for that entire path. So multiply together all the partial derivatives, and then sum together all the paths. So we're going to just find all the paths to a particular matrix. So if we look, for instance, at WHY, WHY has a derivative that comes from the loss down to here, but also to here, and also to here. And it's the same matrix, so therefore what we're going to do is just sum them together. So it may be, for instance, that the loss to this instance of the shared weight matrix is pulling us in some particular direction, whereas the loss here is pulling us in some other direction, the loss here is pulling us in a third direction. And just like all the cases where we have different paths to a weight matrix, where the gradients are pulling us in different directions, we'll just sum them together. But let's look at this in some more detail. So if we look, for instance, at the loss with respect to, let's look at WHY of n, right? That is just going to be the partial derivative loss with respect to y hat sub n times the partial derivative of y hat sub n with respect to WHY of n. And we can look at, in general, the partial derivative of w hy of I is equal to the partial derivative of L with respect to y hat sub I times the partial derivative of y hat sub I with respect to why of I. And then we're just saying that the partial derivative of L with respect to the general why is equal to the summation from I equals 1 to n of partial derivative of L with respect to that particular matrix. So we'll find the partial derivative of L with respect to this w, this w, this w, this w, all the way to this w, all the way to this w, and then we just sum them up. That gives us that. So now let's look at the partial derivative of L with respect to WHH of n. And that's just going to be the partial derivative of L with respect to y hat sub n times the partial derivative of y hat sub n with respect to h sub n times the partial derivative of h sub n with respect to WHH of n. So we've computed the partial derivative of L with respect to Hn, and then from there, Hn to WHH. If we look at the partial derivative of L with respect to WXH, that's the partial derivative of L with respect to h sub n, right, which are these two, times the partial derivative of h sub n with respect to WXH of n. Let's look at a particular entry here, right? Let's look at, so in general, if we have the partial derivative of L with respect to some particular h, we can then get the partial derivative of the loss with respect to some particular WXH at a particular time step, and similarly some WHH at a particular time step. So let's look at how then to just update the loss with respect to an h sub I. So if we are trying to come up with partial derivative of L with respect to some h sub I, well, what do we know? We know, for instance, here, so if we're trying to compute the partial derivative of L with respect to h sub 2, we know that there are two paths leading into here. Right? There's a path coming down from y hat sub 2, and there's a path coming from h sub 3. So we have both those paths we'll need to add together. So we'll look at the partial derivative of the loss with respect to y hat sub I times the partial derivative of y hat sub I with respect to h sub I. And we'll add in then the partial derivative of L with respect to h sub I plus 1 and multiply that by the partial derivative of h sub I plus 1 with respect to h sub I. So no different than we normally do. We just say how many paths are there to here, how many direct paths. There are two outputs, and so therefore we're going to sum together the path going via one output back and via the other output back here. So this will give us this. Once we have the loss with respect to an h sub I, it's easy to compute the loss with respect to an xh sub I and whh sub I. So that's all that backpropagation through time really is just, as we normally do, say we compute the loss by looking at all the paths. And what's going to happen, instead of actually, again, looking at all the paths and summing them up, since that can be exponential, we just go back time step by time step, right? Taking our output activations, figuring out what the gradient is, going, computing this gradient multiple times. That is, we're going to have a gradient at this step, a gradient at this step, a gradient at this step for WHH, and we end up just summing it all together. Similarly for WXH and WHY. That's all backpropagation through time is.